So, hello everyone. Our next speaker is Necdet Duman from Middle East Technical University. Together, we read some fundamental text on model theory, which is a branch of mathematical logic. And today he's going to talk about compactness theorem. And so you can start, Necdet.
Hi everyone. As my mentor said, I will talk about compactness theorem and its applications. So, compactness theorem is an important theorem in model theory, and model theory studies mathematical structures and properties they satisfy. So first, we want to define what a structure is. And in essence, they are just tuples that satisfy some properties. There are some tuple examples. There are some structure examples on the screen. So first example is group of rationals with respect to addition. It is a triple. There's a set of integers as a base set, and binary operation on the base set, and a constant from the base set. So another structure example is field of real numbers, which is a 5-tuple. This time, our base set is real numbers, 2 functions on the base set, and 2 constants from the base set. So pretty much every structure can be considered this way. We can have examples like metric spaces or graphs too, or every sort of example. So to have this definition, we first have to define what a language is. And the language is a set of symbols such that it has function symbols, relation symbols, and constant symbols, and logic symbols and infinitely many variable symbols. So the last part, logic symbols and infinitely many variable symbols, we will most of the time take them as granted, and we will just omit them because they are same in every language. So we won't really write them down. The first order part means we will only consider the properties which quantify over our universe and not over elements of our universe and not subsets of our universe. So there are some language examples here. A language of groups is given here. It has a function symbol and a constant symbol. It doesn't really need relation symbol because we will most of the time think about groups in this language. Another example is language of the ordered sets. We have a relation symbol and nothing else, only logic and variable symbols other than that. There is language of the fields. It has 2 functions, 2 constants, and nothing else. Well, union of 2 languages is a language, and there's an empty language, which is not actually empty because it has logic symbols and variable symbols. So now we've defined the language, we can define the structure. So let's L be a language. A structure on the language is a tuple, where the first entry is called the universe or base set. And rest of the entries are whatever symbol we have in our language, we will have a corresponding object in the structure. So for example, for every function symbol in our language, we will have a corresponding function in our structure. For every relation symbol, we will have a corresponding relations. And for every constant symbol, we will have a corresponding constant. And the corresponding objects for the symbols are called interpretations of these symbols. So we have some examples here, again in the group language. So group language has a function symbol and a constant symbol. So we will have a base set, a universe, a function on the universe, and the constant from the universe in the structures. So the first example is a group of integers with respect to addition. Our base set is a set of integers. We have the usual addition as the interpretation of this function symbol, and 0 is the interpretation of this guy. So this also satisfies group axioms and so forth, but we haven't defined what a property is, so we won't talk about that now. The second example is this guy. We again have the set of integers as our universe and usual addition as the interpretation of the function symbol, but this time we will interpret this constant symbol as 7. So this won't be the group of integers, this won't be a group, but this will be a structure in the group language. And there are a bunch more examples, I will skip them. So now that we have structures and language settled, we can start to talk about properties. And in order to do that, we first need to define what a formula is. And formulas are just symbols put together with some grammar rules. For example, not for example, with logic rules. So we have some formula examples here. This guy is a formula in the group language. Group language has these symbols. And that is because it has symbols from the group language, only the symbols from the group language, and it fits the logic rules. So this is a formula. The second guy is also a formula. It uses symbols from ordered language, and it fits the logic rules. So it is a formula. And these three are not formulas in the group language because the first guy has some symbols which are not in group language, and the other guys do not adhere the logic rules. So those rules and how to define formulas properly, you can find them in any model theory textbook. They're most of the time done cursively. So I won't really give them, but you can find them easily. Now we will only consider some nicer formulas. Formulas where every variable in a formula is quantified. So for example, this guy, there is one variable symbol and it is quantified. So this is a sentence in this language. And this guy is not a sentence because there's a variable and it is not quantified. Being quantified for a variable also means being bound. Those are same things. And this guy is a sentence because both of those are quantified. So we call any set of sentences a theory. There are some theory examples. The first example is a theory in the group language. It has 3 sentences, 1, 2, 3. First sentence will assert that constant behaves as the identity. Second one will assert that there is an inverse element for every element. And third one will assert that operation is associative. The second example is a trivial example. Empty sets is also a theory. Third example is in the empty theory. It only uses logic symbols and variable symbols. And so this theory has the sentences of the form, there exist n things and those n things are not equal to each other. So this theory will assert that for any n, there are more than n elements, which means our structure will be infinite. So theories and sentences are just strings of symbols. So they don't have any meaning, any truth value by just themselves. They need to be interpreted in some context, and structures give us those contexts. So for a theory to have a meaning, to assert something, they need a structure. And also being true in a structure also has a definition, but I won't give that definition. But you can find them in model theory textbooks. So we will now define what a model is. And say we have a sentence in some language and the structure in the same language, then if that sentence is true in the structure, we call that structure a model of that sentence, or that structure satisfies that sentence. We denote it this way. Things are similar with theories. If a structure satisfies everything, every sentence in the theory, then structure satisfies the theory. Structure is a model of the theory, and we denote it the same way. There are some examples here. We have, again, group language and 2 sentences on the group language. First sentence asserts that constant behavior is the identity, and second sentence also asserts something. So we have 2 structures here, again, in the group language. First structure has the base set of integers, usual additional integers, and 0 as the interpretation of the constant symbol. And second structure, again, has the set of integers as universe, usual addition, but this time constant is interpreted as 1. So first structure satisfies this guy, because now this sentence in first structure asserts that 0 is the identity. But then interpreted in the second structure, it asserts that 1 is the identity with respect to addition, which is false. So the second sentence is also true in M1, and I think it is also true in M2. But since this theory has both of the sentences, only M1 satisfies this theory, and M2 does not satisfy this theory. So we will define what a proof is. A proof of a sentence from a theory is finite sequence of sentences, where last sentence of the sequence is the thing we want to prove, and every sentence in between are either something from the theory or something implied by the things before. And this kind of fits with our daily use of proofs. We start with something, we say that this implies this implies that, until we get the thing we want to prove. So now we can state Gödel's completeness theorem. Completeness theorem says that, say we have a theory in the language, in some language, and sentence in the same language, then a sentence can be proven from a theory if and only if every model of the theory is also a model of the sentence. So completeness theorem asserts that being true is actually equivalent to having a proof. It is saying that syntax and semantics are equivalent. And more, not necessarily important, but a corollary that's kind of we are interested in is a theory has a model if and only if it is not inconsistent. So being inconsistent means you can prove a contradiction from a theory. And when it's not inconsistent, you can't prove a contradiction. So now we have a way to test whether a theory has a model. If a theory is consistent, then it has a model. If theory is inconsistent, then it doesn't have a model. So now we can state compactness theorem. Let L be a language, let T be a theory in the language. Every finite subset of the theory has a model, if and only if theory has a model. So this theorem, especially from right to left or downwards to upwards, is very trivial. It directly follows from the definition of being a model. But like from left to right, we need completeness theorem. So well, there's a proof of this theorem in the page. So we want to prove from upwards to downwards. So we assume every finite subset of our theory has a model. Now we will prove it by contradiction. So we will assume our theory does not have a model. Then our theory is inconsistent by completeness theorem, and which means we can prove a contradiction from our theory. And because of the way we define a proof can only use finitely many things from our theory, which means we have a finite subset of our theory which can prove a contradiction. And by completeness theorem, this means we have a finite subset of our theory which does not have a model because it is inconsistent. And this finishes our proof. And the other side, as I said before, directly follows from the definition of being a model. If a structure is a model of our theory, then it satisfies everything in our theory. Then the same structure satisfies every subset of our theory. So this proof was very simple, and compactness can be treated as a simple corollary of completeness, actually. But like compactness has tons of applications, especially in infinitary graph theory or Ramsey theory. And most of the time, the way compactness is applied is the same. So I will just give one example to how we apply compactness theorem. So the application I chose was every set can be linearly ordered. We want to prove that. And to do that, first we take any set, let A be any set. Then we define this language, which has a binary relation symbol and a constant symbol for every element in the arbitrary set we pick. So CR for CA for A in A. Then we will consider the theory, which will assert that this binary relation symbol will be a linear order. And constant symbols are not equal to each other if A is not equal to B. CA, yeah. So now we have a theory. Now we want to apply compactness theorem. So we just have to show our theory, every finite subset of our theory has a model. And to do that, we take any finite subset of our theory. Now, because delta is a finite subset, it has something from this and finitely many of these guys. And because there are finitely many sentences of the form CA is not equal to CB, there are finitely many constant symbols appearing in this delta. And say n many of constant symbols appear in delta. Now we can just take a set of natural numbers. We know that it is linearly ordered with usual ordering. And we know it has more than n many elements. So we can just interpret things that, constant symbols that appear here from 1 to n. And things that does not appear here in any way we want, we can interpret them any way we want, because this delta does not assert anything about them. And now, set of natural numbers with usual ordering and the set interpretation is actually a model of this finite subset. And we kind of showed every finite subset as a model. And thus, we can now apply compactness theorem. And compactness theorem will give us a structure which satisfies this theory, say M. Now, this M has an interpretation of this order or relation symbol, which is actually a linear order because M satisfies this theory, and it has many CAs, and they're not equal to each other. And now we can just linearly order A as A is smaller than B if and only if interpretation of CA in M is smaller than interpretation of CB in M with the interpretation of this guy. And this kind of finishes our proof. So there are a bunch of applications of compactness here. I will try to talk about them as much as I can. So the first application we have is saying there is a structure which has a copy of natural numbers inside, and it has elements which are bigger than every natural number. And also, this structure behaves the same way as natural numbers. Behaving the same way means any first-order property natural number satisfies, this structure also satisfies. So we can virtually do all arithmetic same way as natural numbers, but this time we have things that are bigger than natural numbers. So the second example is how we get actually fields equivalent to real numbers, but they also have infinitesimal elements. So we can do whole calculus and analysis easily without a need for epsilon delta proofs, but just using the infinitesimals we added. And third example is saying that G be a planar graph actually, and K be a natural number. For example, we can pick K as 4 because I think that was proven. Every finite graph is 4 colorable. I'm not sure, I think that was the case. Anyways, so we can prove that if a graph is K colorable, if and only if every finite subset of that graph is K colorable. And another application is access theorem, which is saying every injective polynomial map from Cn to Cn is actually surjective. This normally has a very long proof, but compactness really shortens the proof to 1 page. And there are a bunch of other applications, things I haven't tried too, like I think it is equivalent to Königslemma and some weaker form of Königslemma and some other stuff. So yes, and there are 2 remarks, actually 3 remarks I want to have. First of all, we proved compactness theorem by treating it as a corollary of completeness theorem, but there are other proofs too. So one is a more model theoretic proof called Hankin constructions, where we started a theory, we add every sentence we can write or its negation to our theory. So our theory is huge now. And then we add a constant symbol for every sentence in our theory. Now we also have a huge language. And then we quotient this set of constant symbols to construct a structure which will satisfy this huge, nice theory we constructed. And since it satisfies this huge theory, it also satisfies the small theory we started with. And this sort of constructions are called Hankin constructions. And those huge, nice theories are called Hankinized. There is also a more set theoretic proof by ultrafilters and ultraproducts I won't go into detail. And my final remark is actually the reason compactness theorem is called compactness is because it is analog to finite intersection property characterization of compactness. So compactness theorem is actually equivalent to some topological spaces being compact. There's one example of such topological space. Let L be a language, X be quotient set of all L structures by elementary equivalence. This elementary equivalence means they satisfy the same first order language properties. So the topology generated by these elements as a sub-basis, if that topology is compact, then compactness theorem also holds. So this was kind of my talk. Thanks for your time and attention. And also I want to thank everyone in the program. That was a really great program. I really enjoyed it. Listened to a bunch of great talks and met lots of cool peoples. And I want to especially thank to my mentor. She is also great. So thank you.